All right, let's talk about moments of random variables. So the kth moment of a random variable x about a point A is the expected value of x minus a raised to the kth power. Whoa, what the heck does that mean? Well, I'll tell you what. Let's jump down here for a second. One moment of particular interest to us is the expected value of x. Okay, the expected value of x. And this thing is defined to be, well, we have two cases, the discrete and continuous case. If it's discrete, it's just the weighted average of all the x values, right? You take an x value, multiply by its probability, plus the next x value, multiply by its probability, and so on. Okay? If it's continuous, if it's a continuous random variable, it's the same kind of thing, right? Except that we integrate instead of take a sum, right? It's a weighted average, okay? This is the x part, and this part right in here is the probability part, right? Remember this this f of x dx is really like the chance that x takes on a value between x and x plus dx, right? It's sort of like a small rectangular probability region. But anyway, so this is how we denote averages. Okay. Also, you've probably seen this in a basic statistics class, that the variance of a random variable x is the expected value of the square deviation from its mean. Okay. All right. So anyway, maybe a couple of pictures will help facilitate this a little bit. The expected value of x is the same thing as its center of mass. When you're doing physics, it's the same thing as its center of mass. So if this is a continuous variable and this is the density function then that describes it, it looks sort of like a normal, but it's right skewed, then the expected value of x is probably right here. It's the place where you put your finger in order to balance all that stuff, right? Okay. The variance of x is the expected square deviation from its mean. Okay, so it's some sort of measurement of spread outiness. Okay, so what then, if we come back up to this concept here, a kth moment, if I take the expected value of x minus a to the k, what is that? Well, let's say there's some point of interest to us, a, and then now maybe I have some random variable x, and if I actually observe it a few times, maybe I see it at these places. Okay, then what the kth moment does is it takes essentially it sort of takes these distances. Okay, think of it like this. Finds these distances or differences, right? And then raises them to some power. It might be the first power or the second power or whatever, and then averages those squared or cubed deviations. So it's some sort of an average distance measurement between this random variable x, this random stuff, and this point A. Okay, so let's see where that can come into play here. For example, let's suppose that this will be an application of this stuff up here. Okay, here you have k equals 2. Now I'm going to talk about an estimator, theta hat. Let's suppose that theta hat is some random estimator that we're using to approximate theta. By that I mean, maybe here's some value theta that we don't know but we'd like to know. Maybe it's a population mean. Okay, you can't know the population mean for sure, but maybe you'd like to estimate it with this thing called theta. Okay, and like the sample mean. Sorry, theta hat. Theta hat is our estimator. Okay, whenever we put hats on things in statistics and probability, we're thinking about estimating. Okay, so maybe you can think of this as I've observed theta hat a few times. This is sort of indicating the behavior of theta hat. So here's some parameter. Maybe it's maybe it's a population mean or a population minimum even, and I've got some theta hat quantity, some theta hat procedure that I'm using to approximate this guy. Maybe it's the sample mean, using that to approximate the population mean, or the sample minimum, using that to approximate the population minimum, or whatever. Okay, well then this estimator theta hat has an average. In this picture, it looks like it should be right there in the middle, right? Remember, the average of a random quantity is sort of it's the center of the mass of the thing. So that's probably the expected value of theta hat. Okay. Now, this distance here seems like it would be important, right? The distance between the parameter that we'd like to estimate and the average value of our estimator. And so this distance actually has a name. It's called the bias of our estimator. Okay, denoted by B. Okay, it's the bias. What is the variance of our estimator? Okay, well, by definition, it's just it's the expected value of theta hat minus the expected value of theta hat quantity squared. It's the squared deviation. It's the expected squared deviation from its average. Okay, so it's sort of an average spread outness measure of our estimator from its average. Okay, all right. So we've got a couple things going on here. We've got this. Here's the thing we want to estimate, but our estimator is hitting over here for some reason. Okay, the difference between our average estimator value and the thing we're trying to estimate is the bias. Boop. So it sort of shifted over, and then we have this variation measurement about its center. Okay. Now, what about this thing? What is this thing? This thing is called the mean squared error. The mean squared error. Okay, and here's a fact. Okay, you can prove this. The mean squared error, that's what that quantity is. Okay, it's equal to, or it's defined to be, that expected value of squared deviation between theta hat and theta. Turns out this is equal to the square of the bias plus the variance of theta hat. Okay, so that's kind of a neat result. If you think about that, what is the mean square error trying to get at? It's sort of an average square deviation measurement from our between our estimator and the thing we're trying to estimate. That is, it's sort of an average square deviation measurement this way of our estimator from the thing we're trying to estimate. It's sort of an average distance measurement of these blue lines, sort of. Turns out that thing partitions as the square of the bias, difference between the average and the thing we're trying to estimate, and the variance of it off of its mean. Okay, so this kind of concept is really useful. Okay, it's really useful.